In the beginning, perhaps we were all one. Or rather, it was all one. Since there were no humans, or other creatures, or even matter as we know it. Space-time itself was uniform and infinite then. There was no separate time or space, or dimensions, or matter, or forces like gravity. And then time began. And with the start of time came the beginning of change, separation, differentiation. At first, there was just an unimaginably hot, dense universe, bound together by some kind of super force. Today, scientists recognize 4 fundamental forces in nature, which include gravity and the electromagnetic force that causes magnets to stick to a refrigerator. But, as I've said, in the beginning, there were no separate forces. Instead, the fundamental forces we experience today would have been all unified into a single superforce. Then came the Big Bang, when the universe was less than a second old. Much less. In fact, it was perhaps a hundredth of a billionth of a trillionth of a trillionth of a second old, and maybe 10 billion degrees Fahrenheit. That's when the universe exploded in size, doubling and doubling, over and over again, all in less than the blink of an eye. We tend to think of the Big Bang as an explosion, but it's probably better described as an expansion. Scientists talk about this super rapid expansion as inflation, and that's a very telling term, because the Big Bang and its aftermath can be envisioned more like the inflating of a balloon than like an explosion outward from a single point. In this analogy, the universe is the surface of the balloon. There is nothing else. No air in the middle or outside. The surface of the balloon is the sum total of existence. In other words, the inflating universe didn't inflate into anything. There was nothing outside of the universe, and it didn't inflate around anything. So now, in your mind's eye, just picture what the surface of a balloon goes through when it inflates. Like the surface of a balloon stretching, that tiny newborn universe swelled and stretched everywhere at once, rather than growing outward from some central point. To think about this, imagine you're an ant on the surface of a balloon. As the balloon inflates, the whole thing stretches. Any 2 points become farther and farther away from one another. There's no middle on the surface of the balloon. Everywhere stretches away from everywhere else at the same time, with no starting or ending point. Of course, there were no ants or humans to experience that early inflation of the cosmos. There was no one and nothing. Or there was everything, all combined as one, depending on how you look at it. But at any rate, there were no creatures like us to observe it all. So we have to deduce what happened in those early times. We can do that using the remaining evidence and the best scientific theories humans have put together, drawing on the combined efforts of scientific minds, from Albert Einstein to so many others. But back to that change, separation, and differentiation. In that first instant, that first fraction of a second of the universe, the superforce began to break apart. Gravity disconnected and broke free, becoming its own separate force. And the universe ballooned out so rapidly that we can hardly even conceive of how fast it was, because the time period was so short. And still, only the tiniest fraction of a second passed before that incredible inflation slowed down a little bit, like an explosion whose force diminishes over time. The universe continued to expand, mind you, just at a slightly more sedate pace. And as it expanded, it also cooled just a little. As it cooled, matter formed. Tangible stuff, at least in its tiniest, most microscopic form. But here's the most incredible thing. Matter formed, but not just matter. Matter and antimatter both formed at once. Now, if you're wondering what antimatter is, it's just what it sounds like. Matter and antimatter are two partners, equal and opposite, as it were. When particles of matter and antimatter encounter one another, they annihilate each other, meaning they destroy each other in a burst of energy. Or perhaps we might see it another way, as the matter and antimatter combining to form pure energy. It's also considered possible that more subatomic particles could have formed, like quarks and neutrinos, becoming the building blocks for more matter and antimatter. But back to pure energy. As an analogy, imagine a rainbow. A rainbow is formed when sunlight separates out into the different parts of the spectrum. If light passes through a prism, for example, it's scattered into bands of color, rainbows. These colors of the rainbow are the different parts of the spectrum of light. When the colors combine, say if we remove the prism, the rainbow goes away and we're left with regular sunlight again. We could say, in a sense, that when the colors join, they annihilate each other. They disappear into pure white light, leaving an absence of color. So it is with matter and antimatter. When they meet, they disappear into a burst of energy, like light or heat. Therefore, in that earliest fraction of a second after the Big Bang, matter and antimatter appeared, annihilated one another, and disappeared. But incredibly, it seems that the matter and antimatter somehow became out of balance. For some reason, the matter slightly outweighed the anti. Just slightly. Perhaps one particle of matter survived for every billion that met their antimatter particle and was annihilated. This was an astonishing and wonderful occurrence, because the universe as we know it was born from this imbalance. After the matter and antimatter annihilated each other, that little bit of excess matter was left over, with no more antimatter to make it disappear. This leftover matter is the basis of all the stuff in the universe. That stuff has changed and evolved exponentially since that time. It has reformed in ever more complex patterns, becoming stars and planets and seas and people and everything else there is. But let's get back to that first instant after the birth of the universe. Back to the first appearance of matter. After most of the matter and antimatter was annihilated, the leftover matter was concentrated in little pockets, scattered around the expanding cosmos. These pockets of early matter were nothing most of us would recognize today, of course. There was no air, or water, or gas, or dust, much less planets, or seas, or people. There were not even molecules or atoms. There were just infinitesimally tiny particles of matter that scientists call quarks. These unbelievably minuscule particles now make up the protons electrons and neutrons that form atoms. But at the time, it was still too hot and too dense for these tiny quarks to come together to form more complex matter. Instead, they'd collide and destroy one another, once again creating radiation. As that so young universe kept expanding and cooling though, it soon became cool enough for the quarks to actually stick together, vibrating in complementary and resonant ways. And so they could form into the parts of atoms that we're a little more used to hearing about. They combined into protons, electrons, and neutrons. Still incredibly tiny, but a little more complex. Just a step closer to the world we know. Now, everything we've talked about so far happened within the first seconds of the universe's existence. And as more seconds passed, the cosmos kept expanding and cooling, and more early particles of matter coalesced, until finally, possibly around 3 minutes into the life of the universe, though this timeline has been hotly debated, the cosmos had cooled to perhaps a bit less than 2 billion degrees Fahrenheit. And at that point, the coalescing protons and neutrons could start joining to form the next level of complexity in the development of matter as we know it, the nucleus of an atom. So these particles came together to create the nuclei of the very first elements, hydrogen and helium. At that point, it was a foggy universe, for it was still so hot that these beginning atoms constantly smashed together and broke apart into a haze of particles. This foggy universe has been described as an opaque but very bright environment, a bit like driving through a pea soup fog, where your headlights are reflected back to you from all around. Tremendously bright, but you can see nothing. And still, the universe was expanding and cooling and aging. And now, time began to pass in earnest. It's at this point in the story that we can stop speaking in terms of seconds and minutes and begin to think in terms of years. Many, many years. In fact, hundreds of thousands of years passed before the fog thinned and the universe became transparent. When the universe cooled to maybe somewhere around a toasty 2000 degrees Fahrenheit, conditions were favorable enough for electrons to bind to those first nuclei. And so, they formed the first atoms. These initial atoms were hydrogen and helium, gases that, to this day, remain the most common elements in the universe. Other elements, like those necessary for life, still hadn't formed, however, and they wouldn't form for millions of years to come. But the haze of particles became bound into atoms of hydrogen and helium, and the fog thinned, and light at last could shine. You see, in the early universe, even light and matter hadn't been separate. At this point, though, a few 100,000 of years into the history of the universe, light and matter finally became decoupled. In other words, they separated. Our telescopes today can still pick up that earliest light, drifting to us across the vast distances of space. Over time, that fast light has cooled into microwave radiation. Scientists call it the cosmic background radiation. This radiation gives us important clues about the early universe, and it's powerful evidence to support the theory of the Big Bang. When our instruments detect this ancient light, it essentially allows us to see back in time to the early universe. But we can see no farther back than the time of the first light. Before that time, after all, there was no separate light to linger on for us to see. Still, even after that dawning of first light, in that nearly transparent universe, it remained very dark, devoid of stars and suns. For this reason, the next period in the history of the cosmos can be referred to as the Dark Ages, before the dawn of stars. It would have appeared to humanize like the calm of an endless night, stretching on and on, silent and unwavering, the same in every direction. There were no burning lights in space, as there are today, just microscopic particles drifting and colliding here and there, so tiny we humans couldn't even have seen them, if any had been around. Nevertheless, time went on, and that mostly dark universe continued to grow, and to cool, and change. Eras and ages passed and accumulated. At this point in our story, time stretches to periods that are hard to imagine because of their length. In contrast to the start of the universe, when things happened so fast, it's hard to comprehend just how quickly. So the Dark Ages stretched on, and the universe stretched and expanded. 100 million years passed, and then another 100 million. And still, in the scale of all time, the universe was very, very young. Then, by the time it was, say, a few 100 million years old, that young universe held drift-thin clouds of gas. And these clouds of gas began to feel their own weight. Their gravity pulled the clouds tighter and tighter together until they started to collapse in on themselves. At last, these collapsing balls of gas became furnaces, dense and hot enough to cause nuclear reactions as hydrogen atoms fused together in their centers. These were the first stars, burning bright in the dark vastness of early space. These first stars would have been very, very bright and very, very massive, and they would have endured but a short time before exploding. The first stars must have burned indescribably bright, illuminating the endless night with their fire, until they essentially burned themselves out. The nuclear fusion reactions in the star's centers converted hydrogen into helium until their hydrogen was all gone. Then their centers contracted and became unstable. Then they grew hotter and hotter, and the atoms inside them fused into more and more elements, finally bringing into existence other kinds of matter besides hydrogen and helium for the first time. Elements like carbon could form, the basis of all life as we know it, and also oxygen, nitrogen, and finally, iron. When a star reached that point, nuclear fusion stopped inside it, and within less than a second, it would begin to collapse in on itself again, buckling under the weight of its own gravity. But as the iron atoms in its core were crushed together, their nuclei would repel each other with such force, such nuclear force, that it overcame gravity. And then the star would explode outwards in what we call a supernova explosion, an enormous shock wave that would propel the elements forged in the stars out into space. And so, when the stars exploded, those other types of matter spread across the universe, slowly but surely making possible the world we know today. Then, from the the scattered dust of these fast stars, more and more complex elements formed. And as the age of the universe began to be measured in billions of years, that stardust collected and coalesced, and ever more galaxies and stars were born. The swirling dust and gas formed into more and more new stars, grouped together into galaxies. And as more and more galaxies formed, these grouped together into clusters of galaxies, populating the dark universe with matter and light. Eventually, a cluster of galaxies formed that astronomers now call the local group. Local because it's in our region of space. Within it was born a collection of stars that we call the Milky Way, our galaxy. Then, some 9 billion years after the Big Bang, yet another cloud of gas and dust began to come together and coalesce, perhaps triggered by the force of an exploding supernova nearby. It was one of countless such clouds of dust and gas to come together in this way. But this one, from our point of view at least, was special, because the center of this collapsing cloud became our sun. And around that center, the outer bits of the cloud's matter clumped together into larger and larger balls, spinning through space around the newborn sun. Over time, these collided and joined into bigger and bigger spheres. And thus, roughly 4.5 billion years ago, the planets of our solar system were born. And then, at last, life began on one water-rich planet in the inner part of the solar system, only about 100 million miles from the sun. The first and only life we know of in the universe. And that life evolved and evolved into more and more complex forms of life. At first, there were microbes, tiny, microscopic living things, so small as to be invisible to our eyes. Over time, more microbes emerged that produced oxygen. These set the stage for animal life as we know it, slowly producing an oxygen-rich atmosphere, like that which we breathe every day. Then, eventually, simple animals developed at the bottom of the Earth's wide oceans, such as sea sponges, perhaps 800 million years ago. a short time later, cosmically speaking, just a few 100 million years or so, more and more types of animals evolved, filling the planet's seas with living things. And those sea animals proliferated and evolved, growing ever more complex and diverse and differentiated. And at last, some of them crawled from the sea and set up life on land. And still, those animals evolved and grew, changing and developing ever more branches of the tree of life. Ever more complex life forms spread into nearly every environment on the globe, until one of those life forms gazed at the heavens and wondered, and finally created telescopes and scientific instruments with which to view distant stars and ancient light. That life form, we humans began to reveal some of what came before, to unravel some of the mysteries of the universe, all the way back to first light, and even before, all the way back to the beginning, when all was one. But with each mystery unraveled, we seem to find an even greater mystery lurking beyond. And the secrets of our cosmos continue to stretch the limits of human comprehension. Say that, in the end, the more we think we know, the greater the mysteries of existence. Still, human minds press onward, seeking knowledge and understanding, striving to know the unknowable and understand the incomprehensible, to bring light to ideas that drift among us like the drifting stardust of space. And these ideas, born of myriad minds, join together into even larger and more complex explanations and understandings. These shared ideas coalesce to form something larger, much like that stardust born of myriad stars coalesced to form everything around us, including our minds themselves. And so, perhaps the circle of existence is more like a spiral, building up and up, circling, yes, but also reaching ever upwards in a beautiful progression, like a magnificent symphony of the universe.